Hello students, so today we will do numericals on indirect methods of measuring length, which was explained to you in last two sessions. I hope you have learned the formulae and come. So let us start doing numericals. First sum is very easy. It says distance of moon from the earth is determined by laser method. Okay, you know about that. It is laser light beam at the moon takes 2.5 seconds. So we have been given time. 2.5 seconds is the time taken for the light to get reflected. So T is given. And we are using laser. So we have to use velocity of electromagnetic wave, which is 3 to 10 raised to 8 meters per second, same as sine. So we know how to get distance. Distance is Ct upon 2. This was derived, isn't it? Distance of moon from the earth means like this is the moon, this is earth. So I am sending the laser beam here. So it will travel twice the distance. D is the distance to go, D is the distance to come back. So total distance traveled is 2D, time taken is T. So knowing distance upon time is speed, that is C. So I will get distance as speed into time. So C into T upon 2, because I want only 1D. So we put substitute the value for C, 3 multiplied 10 raised to 8, and time what has been given 2.56 upon 2. So this is the distance. Now we will go to second sum. Assuming that orbit of the planet is circle. So with this assumption, Copernicus determined the radius as 0.36. So the radius, orbital radius, read this word carefully, orbital radius of Mercury planet. So means I have been given orbital radius means distance of the planet from the sun. Okay. We have to find the maximum elongation, means epsilon naught is to be found out. Distance from the earth also. When elongation is maximum, always whenever epsilon is there, elongation is maximum. Now we know the formula. Sin epsilon naught is R distance of the planet from the sun upon distance of earth from the sun. This we have derived last time, that we have derived as such RPS. This is planet from the sun is sin epsilon into 1, because this value is 1. Radius of earth from the sun is 1, so this is given to be 1 AU. In this case, R radius of the planet from the sun is 0.38, so I will cancel at 0.38. You take it inverse, so you will get the value of epsilon naught. So simple. Then distance from the earth, RPE, is cos epsilon naught into 1. 1 comes for because of RES, which derived last time. So we use that formula. Now I know epsilon naught. Substitute the values, you will get the answer. Now third sum is very, very important. See, this is sun and this is the point on the earth. So from earth, moon will be somewhere here. So when the light goes from the earth, passes through the, I will draw again. Okay. This is moon, and we have been given this angle. This angle is given to be 1920 minutes. So this angle is 1920 minutes. We have been given this angle measured to be 1920 minutes. So this angle is given to be 1920 millimeter. Now see, when I will see the full eclipse, when the light goes tangent to from the moon and it comes at the end of the sun, at the diameter of the sun. Similarly the case. So this is the moon, the light is able to come and it is forming a shadow, which we call it, that it shows a dark patch. Is it alright? So we want to find the now diameter of the moon. So this is the diameter of the moon. So I know this angle. So theta is known, diameter is known. So this diameter, what does this diameter becomes? This diameter becomes the basis and this becomes the radius. So radius I want from earth to moon. So earth to moon distance is given. So this radius is given, which we used to call it as S. And now we know basis is equal to theta into S. Therefore theta would be moon diameter upon S. In this case we have to calculate moon diameter. So moon diameter should be calculated. So how much is theta? 1920 minutes. So I will divide by 60 into 60. So now this is in degree. Now this will give me in degree. So degree multiplied pi by 180 will give me in radian. So 1920 I have calculated. So you get this answer. So this is the value of theta. So moon diameter is same this number, theta. Up to here is theta. This is theta. And multiply by, this is the distance of moon from the earth. Distance of moon from the earth, this is S. So this is S, this is theta. So I will get basis, that is moon diameter. Okay. So we will go to next. So let us do the next numerical. The numerical reads, a man wishes to estimate distance of a nearby tower from him. So C is the nearby tower. C is the nearby tower. The man is standing at point A. So man is here. So man is at A, tower is at C. This is ground, horizontal. And now he is seeing actually some distant object, oh, very far away. So that he is looking at the tower and in the background there is some far away object O. He is walking perpendicular to AC. So this is AC. He is walking along AB up to point B such that AB is 100 meter. So this distance is 100 meters. Now when he is looking from A to O and one is looking from B to O, because O is very far away, like suppose there are 2 points which are at short distance and this is a very far away point, then this line and this line, they are almost same line. If you take this point very far away and here the gap same and now you join. So they have become almost the same line. Is it alright? So whenever the point is very far away and we are looking at a very small distance, then these two lines become same. He has given to us O is very distant, direction of BO is same as AO. But find line of sight of C shifting from original line of sight by 40 degrees. So when he was looking at C from A, this was the line. Now when he is looking from B to C, this is the line. So this angle, when he is looking from A to C, it was 0 degree. Now this line are same, but when he is looking from B to C, he is getting this line. So this angle is given to be 40 degree. And by altered angle this becomes 40 degree. Now the question is, actually distance of C from original. So I want to calculate AC. So this is to be calculated. This is unknown. So to take tan of this angle, tan theta. So tan theta would be AB upon AC. So AC would be AB upon tan theta. AB is 100 meter, tan 40, you will get answer 119 meter. So the tower was at 119 meter from A. So see, we have done an indirect calculation. Okay. So then now we go to next question. The angular diameter of sun is 1920 seconds. 1920 seconds. We have done a some similar sum. 1920 seconds of sun. This is the person on earth, this is the moon. And so this angle is given to 1920 seconds. When there are two lines, it becomes second. One line, it becomes minutes. Distance of sun from the earth. Now we are given this distance, sun from the earth. So we are given this distance. So this distance is given. 1.5 10 to 11 meter. What is the diameter of the sun? So he is asking this diameter of the sun. So he has given this distance. So now I have got this triangle. So this is my base. So base is my this D. This S is given. We were calling radius as S, no? So S is given and this theta is also given. So directly we can get D equal to S into theta. Basis is S into theta and S is this number. Theta is 1920 seconds. So 60 to 60 will give 3600. Now this is in degree. Multiply by pi by 180. So I will get in radian. So this radian into this distance in meter. So I will get D in meter. So this is the diameter of the sun. Okay. Suppose there is a planet that revolves around the sun twice as fast. So planet is rotating twice as fast as Earth. So it means it will take half the time. So if the Earth takes X time, planet will take X upon 2 time. So if the Earth takes X days, planet will take X upon 2 days. So now I know the time period. So what would be the orbital size of the planet? Because Earth orbital size I know is 1 AU. Earth orbital size is 1 AU. Because distance of sun from the Earth is 1 AU. Okay. So I will do this Kepler's law. Kepler's law says second or square of the period is proportional to cube of the semi-radius. So T2 square upon T1 square would be A2 square upon A1 square. So I am using 1 for Earth. So this T1 would be X and T2 would be X upon 2. So X upon 2 upon X, so I will get half. So I am getting half. And this 3, this is index is 2. So if I bring it here, it will become 2 upon 3. So half raised to 2 upon 3. And what will come further will be A1. A1 will come now. This index has gone. Come here. So A1 will come here. A1 is 1 AU. As this is in AU, so this would also be in AU. So my A2 would be 0.63 AU. Is it alright? Now we'll go to last sum of this topic. Nearest star to our solar system is 4.29 light years. This is the nearest. How much is this in terms of parsec? So I know 1 parsec is 3.26 light year. So 1 light year would be 1 upon 3.26 parsec. So 1 light year is 1 up, what I can say, 1 light year is equal to 1 upon 3.26. So much parsec. So 2 light years would be 2 into this. So 4.29 light years would be 4.29 into this. So 4.29 upon 3.26. So this is parsec for 4.29 light year. This is, you calculate, you get 1.32 parsec. Now I know this. Then what he says, how much parallax would with this star show? So he is asking theta. When we from two locations on Earth 6 months apart, so when you are 6 months apart, so means as I have shown in this is the Earth's rotation, this is Sun in between. So 6 months means you are here and here, so this distance is 2 AU. So this distance is 2 AU. So this forms the basis. So basis is 2 AU. I hope the revised and come. So this basis is 2 AU and S is given to be 1.32 parsec. So my angle is basis upon radius. So 2 AU upon 1.32 PC. Now both have to be in the same unit. So parsec I am converting to AU. 1 parsec is 1 AU upon 1 minute. So to substitute the value of this, AU will get cancelled. So the answer would be in seconds. So I'll get phi as 1.51 seconds. So this is my angle, parallax angle that the star will show, because from these two locations I am looking at that star. So it is making some angle. So, last time I had explained to you this is the figure. You can have a look at that figure if you want. Okay. So